I'll start this video off as I usually do with a look at Chuck Penson's excellent book, Heathkit Test Equipment Products. And I flip to the chapter on digital frequency counters and multimeters. And I'll start out with the IB-1101, which is a close relative of the one that this video is about. This came out in 1970, costing just about $220 at that time. It was good for up to 15 megahertz. Delivered just in time for Christmas 1970. It was Heathkit's first consumer-level digital product. So that's significant by itself, and was the vanguard of a digital revolution at the company. The circuit uses TTL logic and a 5-digit Nixie display. And here it has a small mistake. It says with hertz and kilohertz indicators and overrange. It's actually kilohertz and megahertz indicators. So that's a bit of an error, I think. Frequency range 1 hertz to 15 megahertz. Anyway, so this persisted for about 3 years, up until 1972, when it was replaced by the subject of this video, the IB-1101. And typically when Heath reintroduced a product later on that was essentially the same internally as something else, they quite often had a number that resembled the original number. Maybe they would add a 1 to it in the most significant digit or something of that sort. So the IB-1101, the subject of this video, is a 100 megahertz frequency counter, and it also was out for about 3 years. A slight overlap with the 101, and of course the 1101 did replace the 101 after the overlap in the catalog. The two units appear outwardly identical. It can be calibrated with nothing more than an AM radio. Circuit uses 26 TTL ICs and a 5-digit Nixie display, and once again it says hertz and kilohertz, but it's kilohertz and megahertz, unless I'm totally screwed up. Frequency range 1 hertz to 100 megahertz. Accuracy plus or minus 1 digit plus, that's inherent, plus the accuracy of the time base. Sensitivity as low as 50 millivolts RMS, and as you go up in frequency, the sensitivity is a little bit higher, requiring 100 millivolts. Gate time of 1 millisecond or 1 second with auto reset. Input impedance 1 mega ohm shunted by 15 picofarads. Maximum input voltage 250 volts RMS, decreasing to 3 volts RMS as you get up near 100 megahertz. Maximum DC input is 250 volts. It has an external standard input, so you can replace the internal clock with an external clock, perhaps one of known accuracy. Discontinued in 1975. Pushed aside by the IB-1102 and IB-1103, which the IB-1102 again seems to be the same meter, but it goes up to 120 megahertz, and the IB-1103 is 180 megahertz and has a more elaborate user interface. And right next to it in the book here is the IM-102, which I've already done a video on. And I wanted this 1101, either that or a 101, as a representative of Heathkit's first frequency counters to go with the IM-102, their first digital multimeter. Anyway, so that's the history up to the point of the product in question. Alright, let's take a look at the artifact. I've got it opened up here. The outer case is physically in good condition, but the paint is kind of a mess, peeling off and chipped and dinged and so on. I'll have to be replacing the feet. This one isn't actually too bad, but if I'm going to repaint it, I need to repaint both halves. And I think I still have enough paint left over from when I did the IM-102 that has the same case that I can paint that up. The bezel seems to be in pretty good condition, but I think this was used somewhere with a lot of nicotine, so I'm going to have to go through here and just get this film of whatever off of there that's covering everything up. The jacks are corroded, the BNC jacks that is, but I don't think they're beyond redemption. They just need some cleanup. If not, I think I can replace those easily enough with new ones. I think they still make essentially the same parts. The rear ones, I did a complete power supply test on this. It seems like it's working, but I'm going to be replacing these 4 electrolytics just because they're really old, just on general principles. But these other ones here, probably not so much. Not going to worry about those too much. These are actually only 10 microfarad radial caps, and I have some of those in my part stock, so I don't need to order those, but I may replace those as well. And I definitely have ordered replacements for all 4 of these from DigiKey, and those are on the way. I've done enough testing to verify that the Nixie tubes are functional, as are the neon bulbs in 4 places. Don't need to replace anything on those. I have put a signal through it and verified that the 7 transistors in the front end signal conditioning circuit appear to be okay. These 2 diodes here, these are clamping diodes, which I've lifted out of the board on one side. Those are just these 2 diodes. So you basically have the input jack, you've got a capacitor to strip out any DC component of the signal, then you've got a resistor to ground that establishes the input impedance, and then you've got a dropping resistor or a current limiting resistor, and then the clamping diodes. And you might say, well, I could just replace those with anything, but these are actually pretty fast diodes, and those would be replaceable, but I found that I could get exactly the same diodes as originally there from an eBay seller, so I've ordered those and waiting for those to come in. I always try to replace semiconductors with the same exact parts whenever possible. I think all the ICs are good. I've got enough signal going through it that I believe everything there is still functional. And I did a test of the oscillator and it seems to be spot on, so I shouldn't even need to recalibrate this. I think it's basically working at this point. I just need to do a little tender loving care in the aforementioned diodes and capacitors. It'll be mostly physical cleanup. I'm also going to be lifting the labels off. Somebody slapped that on haphazardly, and this thing's just ugly, so that's coming off. I'll pull this off, clean it up, and then reattach it a little straighter. The power cord that came with it's intact and usable. I'll clean up some of the corrosion around the inside of the socket here, but that should be about it. Well, I realize that the plastic on this insulator has pretty much just crumbled to nothing. Yep. I'm not sure it was even insulating from ground. Have to do something about that. I was not able to find a replacement for this busted up thing. So what I've got there currently is a couple of fiber washers that have shoulders on them, and the shoulders of the washers front and rear on this panel pretty much touch each other through the thickness of the panel, and then I put a 632 bolt and nut into it, and that goes through the solder lug that's on the wire for the test point signal. So in other words, this screw is electrically insulated from the case, and it doesn't stick out as far as the transistor or the BNC jack, and it serves the purpose of a test point where you can, you know, touch the probe or something there and measure the signal. It does not have the capacity right now to clip something onto it very well, although being a Phillips head and a cross slot at the same time, it could probably be clipped onto with a small alligator clip. If I think of some better way of doing that, I can always change out that hardware. And I've got the top and bottom case parts in the warm soapy bath like I usually do, and I verified that I do still have enough of the special paint I had mixed up that I should be able to paint these case halves without having to buy new paint. Well, after the bath, and I was wiping these down with isopropyl alcohol to get any remaining soap or whatever that may still be on and off prior to putting on a new coat of paint, the paint just started flaking and coming off like crazy. So I went outside with the old paint stripper and a wire brush and worked it over for about half an hour and got everything cleaned off. Just gave it a soap bath. Now I'm going to wipe it down with isopropyl and then start putting on the paint. Alright, with my mini roller, I've got one coat put on covering all edges and a little bit inside the front and rear. That's not so important on these particular clamshells because there is no part of the inside edge that's visible from the outside. Some of the other Heathkit cases did have the front panels inset a little bit, and then you definitely wanted a little paint on the inside, at least for, you know, half an inch or an inch. But I put it on there anyway just because it's easier when painting the edges. So you always get a finish like a roller put it on here, but it's my approximation of a crinkle finish. And the next morning I put on a second coat. Alright, I have all my new electrolytic capacitors here. I've got a couple of Sprague Atom types. These seem to be pretty popular amongst restorers because it's one of the few ones that you can still get from a major brand that are axial in larger sizes. So many of those have been discontinued. 2000 microfarads, 25 volts each, which is the same values as these guys. And this guy was really hard to find a replacement for that had to be within the same length, but for some reason this one's got a really huge diameter. The original's only 25 volts. This one's also 25 volts. Really don't know why it's so fat. These days you'd expect a new capacitor to be smaller than the one it replaces. And it is going to sit a little bit to the side. That's okay. These caps are a bit narrower, so I think it'll still work out about right. And then this Nichicon 22 microfarad, whatever it is, 50 volt, to replace this guy. And then these are both 10 microfarad capacitors, 15 volt, 10 microfarad, 15 volt. And these little Nichicons here, considerably smaller, are 10 microfarad, 25 volts. And these ones I did not buy from DigiKey on this go around. These are just ones I stock. I almost wondered if this electrolytic was misprinted on the wrapper because it seemed like it was way too big for a 500 microfarad 25 volt capacitor, but it is 500 microfarads according to my digital LC bridge. So that's good. Okay, those two electrolytics are in here. Positive pointing inwards, negative to the outside. This guy is in there. Positive this way. And these three guys are all positive that way. And I've verified the connections to the top and bottom sides of the circuit board, so that should all be good now. Well, I tested these three large electrolytic capacitors in my other capacitor meter, one which will read out dissipation. It doesn't give you a direct ESR reading, but it does give you dissipation. And I checked with the typical manufacturer's specs for similar value capacitors and what their D values should be. And on a 2000 microfarad, the charts I found didn't go quite that high, but saying a value of around 0.6 was normal for a lot of just run-of-the-mill electrolytics in a 1000 microfarad part. This one's reading 1.7, so I think that's pretty high. Although it still seems to function as a capacitor, this other one reads open. It's not bulging or anything, but it tested open on both of my digital capacitance meters. It isn't even recognized as a capacitor. So the circuit was running with half the capacitance and the filtering that it should have at the very best, and probably worse than that. Now this is a 500 microfarad, and it tested at 0.6. It should have been no higher than 0.2, according to the tables I looked up online. So I would say it's a good thing that these capacitors are going in the trash. Alright, some 3N bump-on feet have been put on. These are typical of what Heathkit used on their test equipment of this period of time, except they also sometimes use the slightly smaller ones that are about 3/4 as big as these, and that's what would have been originally on here. Unfortunately, those things seem to be pretty much unobtainium these days, so I'm using the full-size ones. And that's the same thing I've used on other restorations of equipment in this same case, and it comes out just fine. It looks okay, it's appropriate. And here's the hardware for putting the handle back on. These are the original trim screws, pretty badly rusted, at least one of them is. And here are two of them I pulled off of something else that I was harvesting for parts to restore other things. They're not perfect, but they're much better, so I'm going to use them. And then the rest of the hardware is in decent shape, so I can just use that without messing around. Alright, let's do a tour of the inside of the case here. A lot of these bits of hardware with plating on them have oxidized, and they've got a fine white powder on them. I've been wiping them off with Q-tips as I notice them. I mean, they're all that way, but I've been trying to mop it up as I work around inside. Anyway, so power transformer here. Looking at the bottom of it, the power cord socket is right here. The ground terminal goes right to a ground lug on the chassis. Another lug goes directly to one side of the transformer primary. The other one comes up here, goes through the fuse, through the power switch, and back to the other side of the transformer primary. The only other things we have on the bottom are the megahertz kilohertz selector switch with all three of its gangs. The one that's separated from the other two is the one that switches the neon, so that has high voltage on it. So then there's This could actually be a 4-gang switch, but it's manufactured with only 3 gangs, and the missing gang leaves a nice air gap for voltage isolation. And the slider that carries the contacts is slotted, so it also has voltage barriers between the gangs. And that switch then wires out to several points on the circuit board, as well as going around to hook up to the neon bulbs. Oh yes, and the input jack is right here, and it is directly wired through this DC blocking capacitor directly to a pad on the circuit board, and the whole front end is right in this area, everything grouped together very closely. Looking at the top, we have the 2 neon bulbs. Yes, those are the ones to indicate megahertz or kilohertz range is currently selected. And then the other 2 neon bulbs are over here, each with their own pair of wires coming from pads on the circuit board to operate them. And rather than wiring directly to the neon bulb leads, which are very small and spindly, the wires go to these intermediate terminal strips, and then the fine wires from the neon lamps go in directly. And it's interesting to note that these bulbs are put in sort of butt end first, with their points sticking out, so they probably figured they'd get better illumination, or an evener illumination, doing it that way. And then these plastic holders keep them in place. There are the 5 Nixie tubes, all identical in sockets. The 5 ICs here are the decoder driver ICs for the Nixie tubes, so they're in close proximity for their circuit board traces to go between the ICs and the Nixie tubes. These ICs here, except for one of them, is one bank of decade counters. Bunch of 7490s. And these ICs here are another bank of 7490s. I believe this is the bank that is actually doing the count, and this is the bank that's the scaling from the oscillator. Pretty sure that's right. There are more of them in that section, and I'm counting 1, 2, 3, 4, 5, 6. There aren't that many in the actual counter that's used for the frequency counter functionality. And the smaller number here is more reflective. Let's see, yeah. 1, 2, 3, 4. I'm taking it back. These are the ones that are actually doing the counting for the display, and these are the ones that are dividing down the oscillator. So I was right the first time. This capacitor here is the small filter capacitor for the high voltage supply for the neon bulbs and the Nixie tubes. These 2 electrolytics are in parallel, and those are the filter for the power supply for all the logic. And this 500 microfarad electrolytic is part of the supply for the 15 volts power source that's used for the analog circuitry, and I believe this cap goes with it, and these 2 transistors handle the actual regulation. The 3-terminal voltage regulator that's on the back of the case is wired down to the circuit board here, and that's the one that provides the regulation for the 5-volt logic supply. So, and then you've got the 2 sets of diodes. This is a full wave rectifier right off the two. They're supposed to be blue, but they've degraded to looking like black or dark gray. These are the two windings, or two ends of the winding, that provides the supply for the logic and the two rectifier diodes. The two yellows are the somewhat higher voltage winding and the two diodes that rectify it. And then the red wire is the one that has the high voltage on it, and of course that's nearby the, well, actually the one rectifier diode and the one small filter capacitor. Small in terms of capacitance, high in terms of voltage. So all the rectifications taking place right here. And then all three windings, the blue leaded winding, the yellow leaded winding, and the red leaded winding, all are tied together inside the transformer and come out with a single black wire that's circuit ground. This is the oscillator section here. 1 megahertz crystal, a tunable capacitor for the time base oscillator that's accessible through a hole in the rear of the panel. Here's the IC that is used for the oscillator. And then these other components here are the other resistors and capacitors surrounding the oscillator IC to make it work. And this trim pot here is the test point voltage level pot, and its wire comes out here to this terminal that isolates it from ground or insulates it from ground, and you can just stick something on there and measure the 1 megahertz frequency at the voltage that's dialed in by this pot, whatever that may be. Now also over here is something that's not associated with the time base, and that's this input sensitivity trim pot, a 10-turn pot, and it's accessible through the other hole in the rear panel that again has nothing to do with this circuit, and you can actually see the 3 circuit board traces that come way down here and end up in this circuit up here. It's tied into the front end of the progressive series of transistors that condition the input signal to get the voltage in a proper range to go into the TTL logic and to shape it to a nice square wave. This is the front end dissipation resistor, and I currently have the 2 fast diodes lifted off the board because at least one of those is shorted out, and that was preventing this circuit from working. I've ordered replacements, and I'll replace these diodes when I get the new ones in. So we come in from that capacitor that we saw on the other side from the input jack, and we have this resistor here to ground, the little one that establishes the input impedance and make sure you have a ground reference after going through the capacitor. Then you've got this resistor in series, and then the 2 diodes to clamp the input to a low voltage. And then right off the bat you're getting into the first stage FET that provides the high impedance, and then the 1, 2, 3, 4, 5 and 6, 1, 2, 3, 4, 5, 6 transistors that just progress through buffering and amplifying and Schmitt triggering. That these 2 guys here are the Schmitt trigger, and then this last one is the final buffer before going into the ICs. And the rest of these ICs here, not counting this one, that's part of the oscillator, as I already said. These other ICs here are just the glue logic, AND gates and so on that are needed for various things. Now these 2 big chips here are the 74100s, and these are dual octal counters, or they're 16-bit counters. And these are the 16-bit latch ICs that hold the number from the counting ICs, the decade counters, and hold them so they can be the information can be sent to these Nixie tubes through the decoder driver ICs. So it's a very logical progression. You count, you latch, you condition and drive, and then you've got the display. It just flows from right to left, and that's the bulk of these ICs. This guy here, this chip is going to be, just because of its position, I'm pretty certain it's the 4-bit latch that does the same thing as these. And I said these were 16 bits. Well, they're not. They're 8 bits. So 8 signals coming in and 8 going out. And this is 4 in and 4 out. But these are all latch ICs. Alright, so I think I've covered all the major components in here. Okay, let's take a look at the Heathkit manual for the IB-1101. Copyright 1972. The usual picture of the unit and the table of contents. Introduction. The Heathkit model IB-1101 frequency counter is a compact, lightweight, solid-state frequency counter, well, solid-state except for the Nixie tubes, that is capable of accurate measurements from 1 Hz to over 100 MHz. One of the many features that make it so convenient and easy to operate is the simple, straightforward design of the front panel. A power switch and a megahertz, kilohertz time base switch are the only controls. The input attenuator switch required in most counters has been eliminated by a specially designed input protection circuit that presents minimum loading to the circuit under test. 510 numeral cold cathode display tubes, meaning Nixie tubes, provide readout at a glance, while 4 neon lamps indicate the overrange, gate, and megahertz or kilohertz functions. Additional features include the rugged and compact cabinet design, the detachable test cable and line cord, and the 5 detent position tilt stand handle. This unique tilt stand handle can be used to position the counter at a desirable viewing angle. When added together in one package, the cabinet design, ease of operation, and exceptional accuracy of this counter combine to make it an invaluable tool for the designer, engineer, or hobbyist. So we have the parts list, and right away there's a fold out with pictures of a lot of the parts to help identify them, and more of the same on the reverse of the fold out, and the rest of the parts list. Assembly notes, and they talk about things like if you have a big fat soldering iron, wrap some copper wire around it and shape to a chisel point to get a finer soldering iron. And some notes about how the resistors and capacitors are called out. And points out that the circuit board is double-sided. So never make a solder connection on the lettered side of the board. Then the step-by-step assembly instructions. Starting with soldering in the Nixie tube sockets, working in roughly 1/3 of the circuit board, then putting on resistors in the same area, some more resistors in another 1/3 of the board, then diodes. Everywhere where there's a diode, they're all put on at the same page of the manual. Then all of the transistors are put on. There's several different types, and they all have different configurations and pinouts, so there are separate diagrams for each type, including variations. You know, you can get a round package or a flatted face package for the 2N3563. And there's a couple of those. And there's actually 3 choices for this other transistor. And then the power transistor, More transistors that go near it. The crystal, the 10-turn potentiometer, the single-turn potentiometer, and there's some sort of a tool that's being made here. 2 tool plates put together. I suspect that's going to be for using these Molex socket strips. So all the IC sockets are implemented and put onto these circuit board positions on these pages. Additional IC sockets, and then the ICs are inserted. And the rest of them are put on this page. Then some things like the trimmer capacitor and the small electrolytics, 10 microfarads. Then a bunch of disc capacitors and a couple of mica capacitors. And then this big mylar capacitor that's used for the high voltage supply, then the larger electrolytics, and a couple more disc capacitors and mica capacitors as well. Now there's another fold out. Chassis assembly, mounting some components to the front, rear, and central chassis, putting on the fuse holder and the label that goes with it, mounting some parts on the rear panel, mounting rocker switches to the front and the fuse holder, mounting the power transformer, and beginning the chassis wiring with the transformer primary, 2 different diagrams and 2 different procedures depending on whether we're doing 120 volts or 240 volts. Then mounting a couple of BNC jacks and some of these terminal strips and the neon bulb holders, putting the lamps into those, mounting them to the chassis. There's another big fold out. One side of it has the chassis wiring on the bottom of the circuit board. Putting a couple of cardboard insulators on the chassis. I presume that there's something on the circuit board that has substantial voltage on it that's really close to shorting out to the front panel. I guess that's why they're doing that. More assembly, mounting the circuit board to the chassis, mounting the front panel on, wiring up things on the rear panel and the neons on the front panel, plugging the Nixie tubes into their sockets, wiring up the power transformer and the mylar capacitor used for the input coupling, building the test cable. Another big fold out. It's still talking about making the test cable and putting in the light shield, which goes behind the Nixie tubes and prevents ambient light from going through the front window, through the Nixie tubes, illuminating internal components, bouncing off and coming back through the Nixie tubes and out the front window again. You don't want to be seeing all that stuff, so you need the light shield. And it also has holes along the top that engage the nipples on the top of the tubes to help keep the Nixie tubes straight. Now the original light shield is long gone. On the similar IM-102 multimeter, which is contemporaneous with this frequency counter, they also had a light shield design, which I created a new version using 3D printing. I may do something similar here. And this is talking about the self-calibration, that you use the cable you've made, plug it into the front input, clip the negative alligator clip to the chassis, and the positive one to the test point, which produces a 1 megahertz frequency ideally. And I'm sure they have some iterative process for self-calibration that way. Warning about high voltages, performing the initial checkout. Final chassis assembly. Putting the feet on the bottom, putting on the handle. The calibration without instruments involves using the oscillator section or the clock section of the frequency counter, which should be oscillating at 1 megahertz, and then tuning a communications receiver to one of the Federal Bureau of Standards stations in Colorado, which transmits frequencies of 5, 10, 15, 20, and 25 megahertz. And you wrap a piece of wire around the antenna of the communication receiver and lay it over the case near the oscillator section. And then you're looking for, I think, beat frequencies to be heard on the radio. And then because you have to tune in one of those stations, and then you're looking for harmonics to create beat frequencies. So that's a fairly clever way of doing it. And then if you don't have a communication receiver, you do something similar with an AM radio. And then if you actually have laboratory instruments available, you can calibrate it using the third procedure. Basically just hooking up a reliable frequency source and then adjusting the frequency counter clock to get a matching readout. 1 page of operating instructions. In case of difficulty, front and rear panel diagrams that go with the operation. Troubleshooting chart. Several waveform diagrams, timing diagrams for the digital logic, a page of specifications, the circuit description on 2 pages, continue it on to 2 more pages of circuit description, and then chassis photographs, bottom and top, the circuit board X-ray view showing both top and bottom foils in red and gray, and then a bottom only, I believe that's bottom only. Actually, I think that's a top view. Yeah, viewed from component side. shows where several voltage measurements can be taken to help with troubleshooting. And then the same thing from the bottom. A Nixie tube and transistor identification and substitution chart. A similar chart for the diodes. And then integrated circuit pinout diagrams. And then the schematic would be there, except I separated it from the manual. And I'll go into the schematic in some detail now. And I put a label inside here explaining that while the frequency counter is fully functional in both ranges, it does have a roll-off where it stops responding somewhere north of the low megahertz range, where it starts getting a little squirrely and then it just stops responding. And that's got to be a roll-off in the frequency response of something early in the counter stage, or probably something in those old components in the front end circuit that conditions the inputs. In case I open this up years from now and wonder why it isn't working at the highest frequencies. Well, I readjusted the sensitivity according to the procedure in the manual, which I'd misunderstood a step in, and now I got it responding up to 25, which is the highest frequency my signal generator can output. I don't know that I can really do any better than that. My Hewlett-Packard analog signal generator can only do 13 megahertz, but since it's reading so nicely up to 25 now, I expect that if I had a higher frequency signal available, it would read just fine. So apparently it wasn't an issue with an aged component. I'm trying to think how I can get a higher frequency in my lab here. I just don't believe I have anything that goes higher than that. Unless I just build a circuit to go faster, but I'm not going to do that. Alright, final views of the fully assembled unit with the repainted case on it. Looking pretty good. Alright, let's do a little demo here. Turn it on, and because I'm in megahertz, the gate is running so fast that it seems to be always on. I'm going to go to kilohertz, and the indication moves to kilohertz, and now the gate flashes once a second, or thereabouts. I've got my signal generator hooked up here, and I'm going to take it down to 1 hertz. And I'm at 1 volt peak to peak. I still don't have the diodes in here, the input clamping diodes replaced, so I have to be careful what voltages I put into this. Okay, I'm going to turn on the function generator, and after 1 second I get an indication of 1.001 kilohertz or 1 hertz. Let's go up to 10 hertz. Go up to 100 hertz. And let's go to 1 kilohertz. Spot on. Let's just crank this guy up to 2 kilohertz. You always have to wait for a couple of gates to come and go before you get an accurate reading. (10 kilohertz). Let's put in 99.999 kilohertz. Just about exactly on. If I go a little higher, I roll it over to 100 kilohertz and it's right on the edge of flipping over. Go just a hair over and now I've got an over range. Now it'll continue to count when it's just rolled over like that and the over indicator is on. The rest of the count is still accurate. So I can go to like that, 100.008 kilohertz, and it'll still give me a decent reading. 0.68 thereabouts. So I can just assume that there's a 1 in this position when the over is on. Unless, of course, I'm egregiously over range. But that is a useful thing to know. So let's switch over to the megahertz range. And now it's going to update much faster because the gate is going many times a second. So I'm getting 0.1 megahertz, which is 100 kilohertz. So let's go to 200 kilohertz. 3, 4, 5, 6, 7, 8, 9, 10. Go up to 20, or 2 megahertz, I'm sorry. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, and my frequency generator tops out at 25 megahertz, so it won't go any higher than this. But very good accuracy on this. Looks like I need to straighten up that one Nixie tube. It's leaning. Actually, these two are leaning a little bit to the right. But that's fully functional. All is working well. Alright, there's the beauty shot. I don't think this really needs a light shield. At least so far it doesn't. Even when I get my light way out here, I'm not seeing anything past the Nixies. So I think it can do without the light shield. I have it dialed into 87.654 kilohertz, and it's just dancing around with 3 or 4 in the last digit, so that's about right. I'm getting a 1-second gate. I've got the kilohertz indication. Now if I go to megahertz, I'm going to just see the 87 part of it, of course. Alright, let's look through the schematic. Start with the power supply. Have a 3-wire line cord, so it includes ground as well as hot and neutral. Goes through a plug, and then conditioned by the fuse and the power switch. Transformer primary is set up so it can be wired either for 120 volts or 240 volts, depending on whether the 2 windings are in series or parallel. And there are 3 secondary windings on the transformer. Let's start with this one first. It's center tapped, and you have 2 diodes coming off the outsides of the winding, which makes for a full wave rectification. It's not a full wave bridge, it's full wave, and that's only possible with 2 diodes because the center tap is grounded. Then we have 2 capacitors in parallel, each 2,000 microfarads, adding up to 4,000 microfarads, so pretty good filtering. And that's applied to a simple 3-terminal voltage regulator set up for 5-volt regulation. And that's either, Heathkit would call it a IB-1101, which is a Fairchild part number, or the LM309K, which is a National Semiconductor part number, and now a TI part number. I don't know if they still make 309s, but they're certainly popular, and if they're not made, they can easily be replaced by other more modern 3-terminal regulators. Anyway, this uses the 309, and its reference point is tied to ground, so the output is 5 volts, and that gives us the 5-volt regulated output, which is used for all the logic ICs, which is the vast majority of the circuit. Then we have the analog stage, which is pretty low current, and that has a similar arrangement: 2 diodes, center tapped secondary winding, making for a full wave rectification. A decidedly smaller capacitor, only 500 microfarads, and that's commensurate with the low current loading. We start out with, they drew it funny, but a Zener diode reference with a current limiting resistor, or excess voltage dropping resistor, actually does both. And it's a 16.1 volt Zener, so you should have 16.1 volts here. There's a small 22 microfarad filter capacitor there to stabilize it. And then you have a Darlington transistor. It's not built as a Darlington, it's made out of 2 separate transistors, but they function as a Darlington. And with the larger, higher current one being the series pass transistor. And with this kind of arrangement, you've got roughly a 0.6 volt base to emitter drop on each of the transistors, so that adds up to 1.2 volts of drop. And if you subtract 1.2 volts from the 16.1, you get essentially 15 volts. So that's a very common circuit, and that's how we get 15 volts regulated. It doesn't have feedback. I'm always reluctant to call it regulated if it doesn't have feedback, but it's at least a reference voltage approximating 15 volts. And within reason, it should hold that voltage. Then finally we have a winding with one side of it tied to circuit ground, the other side going through a half-wave rectifier, a single diode, and then a small capacitor to ground. This is a higher voltage capacitor, though it's not one of these, 25 volt electrolytics. And you end up with a somewhat filtered, and with the small size of the capacitor, it's got quite a bit of pulsation on it. But the winding voltage here is not mentioned on the schematic, but it can easily be figured out. And you end up with roughly 170 volts unregulated, and that's the high voltage power supply for the Nixie tube display and the neon indicator lamps. The basic principle of a frequency counter involves having a gate and a counter, and then counting input pulses from whatever frequency you're measuring for a period of time defined by the gate. If the gate is only 1 second long, that means you're allowed to have the counter accumulating count for 1 second, and that can be translated into the frequency. By the same token, if you're trying to measure higher frequencies, you need a shorter gate, and that's the basis of the frequency counter. You have to know how big your counter is and what your gate period is, and the rest can be worked out pretty directly. So let's start with the time base. This has got just a simple 2-inverter clock using a 1 megahertz crystal. It's, the classic configuration. Each of these 2 NAND gates here is operating as an inverter. And if you have 2 inverters chasing their tail with a resistor from the output of 1 back to the input, and then some sort of an element that can perform a time constant, either an RC network or a crystal in the feedback circuit, you can get it to oscillate. In this particular circuit, these 2 resistors are here to help. It's essentially biasing the logic into a voltage range that it's not really designed to operate in as a digital device. Even though these are TTL logic chips, if you can force them to try to sit at some point that would be considered their linear region instead of their digital purely on or off region, that can get them to operate a little bit like an analog device, and that helps them operate in an oscillator like this. But the output is still turning on and off, and it's buffered by this inverter, and that gives you a nice square wave output. These 2 capacitors are here to provide a capacitive loading for the crystal, which it needs to operate reliably. And one of them is a fixed capacitor, the other one is a trim capacitor, and that allows tweaking the frequency of oscillation slightly. The crystal wants to operate at 1 megahertz, but by changing the capacitive loading, you can force it to go just a hair faster or slower than that, and that's how you can trim it. This is pretty conventional circuit. What makes this a little different is that you can also replace this clock with an external clock of 1 megahertz, and it's capacitively coupled, and it overrides what this is trying to do and just forces its 1 megahertz straight through and out. And that can allow you to use some laboratory standard frequency sources, which might be slightly more accurate or more stable. And that's really the main thing. Is one of the things that separates the men from the boys when it comes to frequency counters isn't so much how fast they can count or how high of a count they can achieve or what resolution they can get. It's really how stable are they. Yeah, you can dial it in, but then what if the temperature changes a little bit and the component values shift a little bit? The crystal isn't 100% stable, it's temperature susceptible. And so the less expensive units that just have an oscillator like this, they'll give you readings that are very slightly off on hot days or cold days. And the more expensive professional frequency counters have oven-controlled crystals. So the crystal's held in a small chamber with a heater, and a circuit monitors the temperature and adjusts the heater to maintain an accurate temperature, and then you calibrate the oscillator for the desired frequency at that crystal temperature. And so this is not an oven-controlled oscillator here, and for that reason the rest of the circuit might be just perfectly fine. It is just digital after all. There's nothing else calibratable in it, but you might plug in a laboratory standard 1 megahertz signal here, which is coming from an oven-controlled oscillator, and thereby get better performance. So we have a 1 megahertz clock coming into this, and this frequency counter is set up to read in a kilohertz range and a megahertz range, where the maximum count is 99.999. So if you envision 99.999 kilohertz, that's going to represent a count of 99000, with the decimal point being implied. The decimal point is not derived by any logic, it's fixed in place. Therefore you need to have a counter that can go this high, and if you're considering everything to the left of the decimal point to be in kilohertz, that means that this represents a 99.000 kilohertz reading. Well, if you're going to come in with a clock of 99 kilohertz and you expect it to be counted up to a count of 99000, that means you have to count for 1 second. Because what's this mean after all? 99 kilohertz means 99,000 cycles per second. So if you're only measuring for 1 second, then you will get a count of 99000. Stick the decimal point in and interpret it as kilohertz, and that's what you've got. And that's what the frequency counter is essentially doing. Now what about megahertz? The display isn't any different, the counter isn't any different. It can still display 99.999 actually as its maximum count, but here I've got it written as 99000, so a little bit less than the full count. If you're going to come in with megahertz and expect it to count up to that, you need to count for 1,000th of a second, or 1 millisecond. So you need a gate of 1 millisecond duration, or a gate with a period of 1 millisecond, to be in the megahertz range, or megahertz mode more correctly. And in the kilohertz mode you need the 1 second long gate. So that's what we're going to be achieving here in the next part of the circuit, which is the prescaler. Probably I should just call it the scaler. That would be more accurate than calling it prescaler. And it's consisting of 1, 2, 3, 4, 5, 6 decade counter ICs and a JK flip-flop. Each of these ICs is really 4 flip-flops chained one after another, and by tapping off of their outputs at various points you can actually get a BCD output. And the decade counter is set up with BCD terminals, but they're only using the A on here. And what actually is going on is, if you just look at the first of the 4 flip-flops in here and take its output, that's called A, and that's in the ABCD binary weighting. So it's essentially a divide by 2. And then the other 3 flip-flops, I should say, that follow that are configured as a divide by 5. So a divide by 2 followed by a divide by 5 gives you a divide by 10, and that's how we're knocking the 1 megahertz frequency down in orders of magnitude. And you can see here that the A output is wrapped around to this input, which is the input to the following 3 flip-flops. There are also programming pins on these decade counter ICs, which is a 7490, a very classic TTL part. There are 2 inputs going into an AND, and they're called R0 input 1 and R0 input 2. And so those are ANDed together, and those force the internal flip-flops to a 0, 0, 0, 0 on the ABCD output, so a binary 0. There's also 2 more inputs, R9 input 1 and R9 input 2. Those are ANDed together, and those will force, if that's logically true, it will force the internal flip-flops to assume a value of 9 in BCD, which can be useful for some things. The way the IC is set up is if either of the 2 inputs in a pair, in other words, the pair consisting of R9 input 1 and R9 input 2, if either of those are tied to circuit ground or 0 volts, then the logic inside of here doesn't care what the other one is doing. So Heathkit actually takes advantage of that. They have R9 input 1 and R0 input 2 probably selected just for whatever is the most convenient with the circuit board traces. Those are tied to ground. Therefore, the other R0 input and the other R9 input are don't care inputs, and Heathkit literally leaves them floating so they could be 1 or 0 or in between, whatever, because their pairs, their complements are being grounded. It doesn't matter what goes on with these. There's no point in tying them to anything. Just let them float. And likewise, we're using the A output, but the B and the C, for example, are not used. But the D, which is the sort of the overflow of the counter, goes on to the input of the next one, and so on. I've only penciled in these extra pins because Heathkit did not, and they did some poor drafting things here where they have pin 10 shown, and they also show pin 10 wherever it's at down here as ground, so they're showing ground twice. That's bad circuit diagram practice, so I've crossed it out here for my own understanding. Really, these are the 2 inputs I already mentioned. They're grounded, and the other things are left floating, and we've got the A output tied back into the other clock input so that it will chain all 4 counters together and make them act as a decade counter with a BCD programmed output, and the overflow goes into the next one, and the next one, and the next one. So what that means is you have 1 megahertz coming into here. You divide that down, you've got 100 kilohertz. Divide it down by another order of magnitude, it's 10 kilohertz. Divide it by another order of magnitude, and it's 1 kilohertz. And as I already pointed out, if you're in the megahertz mode, you want to have a gate that is 1 millisecond long, and that's the reciprocal of 1 kilohertz. So 1 kilohertz, if you actually divide that by 2, you'd get half of a kilohertz, or 500 hertz, but the period of the pulse, the time when it's on as opposed to off, is actually 1 millisecond long. And so that's being used as the gate signal if you're in the megahertz mode. And here's the switch. In megahertz, we tap off the A output of this decade counter. So just think of it as this divided by 2, and then using half of that, because we're only looking at half the waveform when it's logically high, for example. So that gives us our 1 millisecond gate for the megahertz range or mode. Now we divide by again, we've got 100 hertz. Divide again, you've got 10 hertz. Divide again, you've got 1 hertz. And that's fed into a separate JK flip-flop, and only the Q output is being used. That's logically the same as what we did over here when we're taking a look at the output of the first flip-flop in the set of 4 here. So if you just consider that we need to replicate 1/4 of this IC over here, it's just done with this flip-flop, and you get the same thing. And its output is 1 second long, which is the appropriate duration when you're in the kilohertz mode, and hence it goes to the switch. So the switch picks off one of those 2 periods, and that's called the gate signal, which is up here, and it even says gate. Well, the next thing we need to do is condition the input. This has a wide range of inputs that this frequency counter can accept. In certain frequency ranges, it can accept inputs of a couple hundred volts. And as the frequency goes up, it has to be a lower and lower voltage till, if you're up around its maximum frequency, it can only be a couple volts. So the job of this circuit is to condition whatever voltage input you're putting in and whatever waveform it may be, and whether it's positive only or negative only or bipolar, in other words above and below ground, it all needs to come out of it a square wave that's compatible with TTL logic, and this is done in several stages. First thing, we come in with the input and we strip out any DC component and then ground reference it with a 1 meg resistor. That gives the input a 1 mega ohm input impedance. It also ground references it, so regardless of what's going on out here, the input here is wiggling above and below ground. And then we go through a series resistor. It's 3 watts, so it's expecting to dissipate a bit. And then 2 diodes side by side, inverse parallel to ground. So this point can't really get much more than, a fraction of a volt above and below ground. So the first thing we've done is, regardless of the input voltage, it's been clamped down to a fraction of a volt above and below ground. And this capacitor here is to help this work a little better at higher frequencies by bypassing a bit of this resistance. The first stage is 2 transistors. It's actually an FET, and FETs have incredibly high input impedance. You don't want any current actually going anywhere once it gets in here. So you're presenting this conditioned input to the gate of the FET, and it's just set up as a source follower. The drain is connected up to the plus 15 volt power supply through a variable resistor and a couple of resistors outboard of that, which limit how much this can be adjusted. And that's for the input sensitivity. You can mess around with the input sensitivity as required to get the best overall response to different voltage levels. But basically all this thing here is doing is providing a very high input impedance, and then after it, it's a very low output impedance of this stage, but doesn't change the voltage levels at all. It's got a gain of near unity. Now we're following that with a very simple amplifier. The voltage here having been knocked down so much, just a little bit above and below 0, we're amplifying it with this simple transistor amplifier. So now we're bringing up the voltage that's been lowered so much, we're bringing it back up to a more reasonable amplitude, of a more known value. And then we follow this with a Schmidt trigger over here, but the Schmidt trigger needs to be buffered from this, so there's an additional transistor put in here which has no gain. It's just acting as a buffer. So once again, we just clamp the heck out of the input signal, reducing it to no more than about 0.6 volts above or below ground. We buffer it, then amplify it, and then buffer it again, and then present it to the two transistors that are in the Schmidt trigger configuration. I'm going to talk about that now. And I actually wrote a paper on two transistor Schmidt triggers, and I adapted it here for PNP transistors, bipolar or BJT PNP transistors. I was more familiar with this circuit before in an NPN configuration, but really you're just turning everything upside down and reversing the polarities and that kind of thing to turn it into the PNP. So I have this sketch here, and I'm going to just basically recite what I wrote down, and therefore I won't screw it up so badly if I was trying to improvise what I'm going to say about this. You have an input voltage, a PNP transistor here, another PNP transistor here. The emitters of both transistors are tied together, and through a resistor we're going to call RE to V+, which in this meter is plus 15 volts. Then there's a resistor called R1 here, which goes to circuit ground or the 0 volt level. There's the second transistor has its base pulled to V+ through a resistor called RB, and then that's connected to the collector of the first transistor through a resistor called RA, and then finally there's a resistor called R2 that goes from the collector of this transistor to ground, and the output is taken from this point. And the purpose of a Schmidt trigger is to put a snap action onto a slowly changing waveform. If you're going into logic and you've got a waveform that's drifting around in voltage, it may be a sine wave, it could be a slow changing DC level, whatever. You can't have that kind of sloppiness going into a logic circuit. You need to clean it up so it has sharp transitions from low to high and high to low. And you also want some hysteresis, which means that the point at which the logic treats the signal as high and when it treats it as low again are different levels. So let's pretend we have an input voltage. It's some high value, you know, a few volts, whatever, and it's slowly decreasing. Then it's going to stay that way, and then it's going to come back up after a while. You want to maybe take it down to this point we'll call VP. At that point, the output of the Schmidt trigger will transfer to its other state, high to low or low to high. In this case, I drew it going high to low. And then at some point, when the input voltage drifts back upwards, you want to have it go past the point when it transitioned going in the other direction. So it can't just come back at this point. You need to go past it, in this case a little more positive, before the output is allowed to switch back to its original state. The difference between this level and that level is the hysteresis, and that prevents its chattering. For example, what if you did not have the hysteresis and you only had one threshold, and that applied to both signals going low and signals coming high? It's the same level. What if the signal just hovered right around that threshold? Then just the tiniest amount of noise would cause the output to be chattering on and off, on and off, on and off. You can't have that. So you force it to be going past a certain threshold to turn on, then going past that threshold in the other direction in order to turn off again. So that's what the Schmidt trigger is trying to accomplish. So I'm going to go to a post-it note version of this while I talk. Get the camera all stable here. So suppose the input voltage here is somewhere relatively high. It's closer to V plus than it is to ground. And we'll just say it's up near V plus for the sake of this argument. Since this is a PNP transistor and this input is so far in this direction, the PNP can only turn on when its emitter is a higher voltage than its base. But if the input is way up here, then you've got the voltage drop across this resistor that's separating V plus from the voltage here. Therefore, you pretty much guarantee that the base is a higher voltage than the emitter. Therefore, it's turned off. So we'll say T1 has no base current, so it's off. Meanwhile, you've got T2, and it has a voltage divider from V plus through RB, through RA, and through R1. So you have some voltage here, and it's probably a lower voltage than V plus up here. So that would turn T2 on. You've got emitter to base current flowing through RA and R1 from the emitter here, and that's enough to turn T2 on. And not only is it on, it's fully on, it's saturated. That means that the voltage between the emitter and the collector is essentially zero voltage drop. This is turned on almost like a short circuit. So that means its output is essentially sitting at whatever the voltage divider is between this resistor, RE, and R2. If this is acting like a short, you've got a voltage divider from V plus through RE, through R2, and to ground. So you've got a voltage divider, and depending on what those resistor values are, you're going to have a certain voltage here resulting from that voltage divider, and V output will be at that voltage at this point in time. Now let's suppose that the input voltage starts to decrease. It's not so much up near V plus anymore. It's starting to come down. T1's emitter is being held fixed by the current flowing in T2. Remember that we've got this transistor turned fully on, it's saturated, we've got this voltage divider, and therefore we have some current going this way, and that means there's a certain voltage drop across this resistor, and it's not changing. Therefore, this emitter is held at that same voltage, and with V1 decreasing at some point, it's going to become less than the emitter, and it needs to be not just slightly less, it needs to be at least 0.6 volts less than the emitter in order to overcome the emitter base voltage drop of the transistor. So when V1 reaches 0.6 volts below the value here at the emitter, we'll call that the VP mark, and that matches the sketch I made. When that happens, T1 will start to get some base current going on, and therefore it's turning on a little bit. It's starting to turn on. As it does so, the voltage across R1 increases, because now we not only had the current going this way, which caused a voltage drop across R1, now we also have some current going this way through the transistor, which is now turning on, and that current is added to the current that's coming this way. More current across the resistance means more voltage drop. With the voltage here increasing, that means there's less emitter base current in T2. Remember that the reason for it having current going from the emitter to the base is because we had this unimpeded path, but now we're building up a voltage here. This point is rising in voltage. It's getting nearer the voltage here, therefore there's less emitter base current flowing, and it starts to turn T2 off a little bit. It's no longer in saturation. The voltage here starts to rise, and that's because the current changing the way it does, and you apply Ohm's law to it, it's going to rise. But this increases T1's base to emitter voltage. Remember that the two emitters are tied together, so if the voltage here is rising because of what's going on here, then the voltage here is also rising. And with this rising and this falling, that means that it's encouraging this transistor to turn on even more. And when it does, it steals more current from here. The voltages swing even more, and it's like a snap action. It crosses that threshold and suddenly, bang, this transistor is off, this transistor is full on in saturation. It just switches that quickly from this one essentially being off and this one in saturation, and then in a blink of an eye, this one's off and this one's in saturation. And that's a form of feedback. It's positive feedback. It snaps the circuit into a state where T1 is on and saturated and T2 is off. And if this transistor is off, now this is a very high impedance. It's like this point isn't even connected to here, and therefore you just have this resistor, which is usually a pretty low value, pulling this point down to ground. So you've got essentially 0 volts here instead of the point it had before that was based on the voltage divider from here to here. So looking at this diagram, we've accomplished this much. The input has come in, it's drifted down, it's crossed VP threshold, and the output, which was at some voltage determined by the voltage divider, suddenly snaps down to essentially ground. A very short, abrupt transition, which is what we're looking for. We're trying to square up a sloppy, slowly changing waveform and turn it into a very crisp digital waveform. Now let's suppose that we've been in that state for a while, and now the voltage input starts to rise back up towards V plus again. T1's emitter voltage is now controlled by its own emitter current. Remember that with this one off, it's out of the picture, and now all the current from here is going this way. Now you've got the voltage divider comprised of RE and R1, and the voltage on here is at the middle of that, more or less, because this is fully on. It's like a short circuit, and we just have these two resistors in series, and this voltage here is essentially in the middle of that somewhere, depending on the resistor values. So as I said, T1's emitter voltage is now controlled by its own emitter current, and of course that's taking into account the voltage drop across RE. When V1 has risen to a point about 0.6 volts below whatever voltage that is, and we're going to call that Vn, as I have it partially obscured there. And if you pick your resistor values right, then that voltage we're talking about here will be higher than the threshold that we had going the other direction. So when Vi has risen to the point where it's slightly higher than 0.6 volts below this value, Vn, T1 will start to turn off. It doesn't have enough emitter base current going on anymore. This allows our T2 to start turning on a little bit again, adding its own emitter current to T1's, therefore changing the math, and you're nudging the emitter voltage downwards due to the increasing drop across RE, and this compels T1 to turn off more quickly. Again, you want that snap action, and that's due to its emitter base voltage decreasing. And once again, the positive feedback snaps this circuit into the opposite state, where T1 is fully off again and T2 is fully on, saturated. And that causes the output to snap back to a higher voltage again, just like this. So that's the essence of how the two transistor Schmitt trigger works. In the actual Heathkit circuit, they've changed it a little bit, augmented it. I haven't worked out all the details of the math on it. I'm too lazy. This is the same exact configuration I just had in my sketch, except that they've added two diodes in series to R1. They put them there, and that causes an additional voltage drop there, which does not change based on anything else going on in the circuit. And I'm sure that's why they put that in there. It's a refinement of the circuit which benefits it in this particular situation. And then RA here, they wanted to have a fixed amount of voltage drop across that instead of a varying voltage drop. So they replaced that resistor with a Zener diode. So you're going to have some voltage drop across this resistor, that's RB, and you have some voltage drop across here, that was R1, but the part in the middle is always going to be 4.7 volts. So again, a refinement makes the circuit work a little mo better, right? And then finally you have that nice squared off waveform, and recalling what we did, we took an input that's voltage could be all over the map, and it might be one polarity or another. It may be above or below ground. It may have a DC component to it. We strip off the DC component. We knock the voltage way down. We build it back up. We buffer it. We Schmitt trigger the heck out of it. So now it's squared off, and the output voltage is known because we know what the resistor values are above and below the transistor Q2. In this circuit it's called Q6, but Q2 in our sketch. And then all we have to do to really make it user-friendly is buffer it one more time. Now this is just a simple emitter follower here. It doesn't add any gain. It's just a buffer. And that tells us that the resistor values that were used here for RE and R2 had to be selected so that the voltage swing out here would be in line with what a TTL logic circuit requires and expects of its input signals. So I hope that was a little more clear than mud. Well, now we have a bunch of counters. And they're the same kind of counter chips that were used down here, 7490s. There's 1, 2, 3, 4 of them. And you may say, Paul, something's goofy there, because I had this sketch that said we're counting 5 digits. 1, 2, 3, 4, 5. Or a count of 5 digits looking at it this way. So how come we only have 4 decade counters? 1, 2, 3, 4. Well, we actually have another one, and it's here. And you may remember when I was talking about what's in these things, it's essentially 4 flip-flops combined in such a way that they act like a decade counter. And that requires some fancy feedback between various stages. But here are 4 flip-flops. They're different models of IC. The first 2 are part of the same IC package. It's IC24 Part A and Part B, 2 identical flip-flops in one IC. And then there are 2 more ICs of which we're only using, well, it only has 1 flip-flop each, but they have multiple inputs, which we don't need here. But this particular chip that they selected for this does have more inputs that we just have dialed out or canceled out by, ignoring them or tying them to the V plus voltage or whatever. And they're combined in such a way that you can see this input is wrapping around from an output here, and this point, which is an output to an input, is also brought over as an input here, and that's because you're trying to get it to count up in BCD and have a maximum count of 10. So what's that boil down to? Well, these 4 flip-flops are exactly what's going on in one of these decade counter chips. So it's really just, you can think of this as being an additional decade counter chip. Therefore, we do have 1, 2, 3, 4, 5 decade counters, which corresponds with 5 digits in the display. So why isn't this one just using, why are 3 ICs being used where one could do the job? Well, these decade counters are also chained together, just like these were. The output of one goes into the input of the next, and then it overflows to the next, overflows to the next, overflows to the next. Therefore, whatever frequency is coming through here gets lower and lower and lower every time it gets divided down by 10. So if you have a high frequency here, by the time it's gone through here, it's a tenth of what it was. It goes through here, and the overflow is a tenth of that. The overflow here is a tenth of that, and so on. So the highest frequency this chip receives is orders of magnitude away from what the highest frequency that might be seen over here. These flip-flops were selected because they have a higher speed. They're rated for a higher speed of operation than the 7490 is. Now, later versions of the 7490, they're still made today, but these are plain vanilla original type. Well, that's not absolutely true. They're actually Schottky types, I believe. I can check that real quick. No, they're not. These are plain vanilla 7490s. They're not even the Schottky version. And they're not rated for very high frequency. The spec sheet for a 7490 is only about 30 megahertz. But we have a counter here which, in theory, could go up to at least 100 megahertz. These are not fast enough. So these are faster chips, and they can work faster. But interestingly enough, I looked up the exact part numbers that Heathkit stipulates in their manual for these ICs, and these have only a 30 megahertz maximum recommended frequency of operation. From batch to batch, example to example, they may work a little faster than, another one might be a little slower, but they don't recommend them being used any higher than 30 megahertz. Well, that's kind of interesting, because, if you're feeding in a 100 megahertz signal here, which is what this thing is technically rated for, this point here is going to be seeing 100 megahertz. None of this changes the frequency. So I'm scratching my head over that, and I really don't know the answer. I thought certainly they must be using a different version of the chip, but it's just, a 74L or a 74S. It's the Schottky version of the chip, and I looked up 2 different manufacturers' spec sheets, and the maximum recommended frequency is only 30 megahertz. Actually slower than these chips. So I don't know. They must be able to go faster than that, or the circuit wouldn't work. But the other thing is, the characteristics of these chips can change with temperature, they can change with age. Parts that used to be fast might not be fast anymore. And since this is quite an old meter that I have here, decades old, I suspect that this frequency counter no longer works up to 100 megahertz. It's rated kind of vaguely as at least 100 megahertz, and that's because they don't know how high it can actually go, depending on which chips are in it and the temperature and you know, age and all sorts of other things, I suspect that this frequency counter maybe can't get anywhere near 100 megahertz these days, but we'll see when I test it out. Anyway, so that's the whole thing. You're dividing it down a bunch of times, and unlike down here where we're not really interested in the outputs except for the D output, which is treated as the overflow, here we're picking off all 4 of the bits in the BCD pattern, A, B, C, and D, or if you want to look at it by the binary weighting, A would be a weighting of 1, B would be a weighting of 2, C would be a weighting of 4, and D would be a weighting of 8. So you've got a BCD pattern coming off the first decade counter that's comprised of individual flip-flops. Then you've got your ABCD coming out of the next order of magnitude down. And the same thing here, and the same thing here, and the same thing here. Always taking the overflow from the D output and feeding it into the toggle input of the first flip-flop in the internal chain. And just like we did here, we can segregate the internal flip-flops into a divide by 2 followed by 3 flip-flops acting as a divide by 5, and you can't get from one to the other unless you go out of the chip, wrap around, and come back in. And that's the same exact thing that's happening here. The A output is always wrapping around back into the input that feeds the next set of 3 flip-flops. That happens over and over and over. So again, we're not doing anything remarkable here. Let's look at the presets resets. A typical flip-flop here, the R9 inputs 1 and 2. One of them is not connected, the other one's grounded. So it's not doing anything. It's not going to try to set this to a count of 9. And the reset to 0, one of them is tied to plus, logic high. That means that the other one is paid attention to. If this one were tied to ground, then this chip would not care what this one's doing, but because it's tied to logic high, now it does care what the other one's doing, and these are all tied together, and this is the reset pulse that comes from some other logic I'll talk about later. Obviously you have to reset these counters sometimes. Down here we did not have to reset the counters because they're free running. They just count and count and count and reset and reset. You know, they count as high as they can, then they reset back to 0 and repeat, repeat, repeat. But here you have to count up during a gate period, then stop counting, display what the count is, then reset, gate it again, count up again during the gate, and repeat. Now one thing that's a little interesting here is the 2JK inputs to this very first flip-flop in the chain of counters are tied together, and they're going down to the mode switch. And again, this is going to have a 1 millisecond pulse on it if you're in the megahertz mode, or it's going to have a 1 second pulse on it if you're in the kilohertz mode. And that is directly coming over here and feeding the input to this. So we're not actually trying to stop all the counters. All we have to do is stop the very first stage, and therefore the rest of it will stop along with the first stage. These can't count if the first one isn't doing anything. And that's how we determine whether the counter is running or whether it's stopped. Now, being stopped is not the same as being reset. There's an interval between stopping the count, then storing the results of the count somewhere so that it can be displayed, then resetting the count, and then counting up again. Therefore, we need more than just, well, I should go back for a second. This is a positive going reset pulse that's going into the reset to 0 input of all these decade counters, but the flip-flops over here are a little different. They don't have a single input to treat like that, so they also need a negative going pulse to reset, so the logic down here develops a negative going reset pulse. It's just the same as this one, but it's going low to reset instead of going high to reset. And those are tied into the clear inputs of all 4 of these flip-flops, achieving the same thing as resetting a regular decade counter. Now, like I said before, we have to store the information immediately after stopping the count. And you've got 1, 2, 3, 4, 5 sets of BCD data coming out of these counters, and there are some latches. It calls it memory here. That's, yeah, technically, but really they're just latches. There's 8 bits of latch in a big IC, another 8 bits of latch in another IC, and then a 4-bit latch to handle the additional digit. And those are all tied together. Heathkit, stupidly here and very confusingly, showed a single pin with the numbers 12 and 23 on it, implying pin 12 and pin 23. Well, that's not the way you do this. You show separate pins as separate pins. Bad drafting practice, Heathkit. Who signed off on that? Anyway, so I've redrawn it here as those two, as being 2 inputs for the tied together though, and they also show the signal rippling through here, so it's only applied here, and you're supposed to know that it passes through this chip and goes into this one. Well, that doesn't actually happen. The signal does not go through the ICs to get to the next one. So another black mark on Heathkit's drafting in this particular schematic. You have a circuit here, and it's called transfer, and it comes around and it goes to the control pins on this latch, these latches, and these latches. And what that's doing, that transfer pulse is generated shortly after stopping the count. So whatever count is in them now gets locked into these latches, and then the transfer pulse goes away, so whatever's in here is held there and does not care what the counters are doing anymore. And then shortly after that we issue the reset pulse, get them back to 0, and then right after that we give it another gate and allow it to count up for a new count. And that whole thing repeats over and over. The outputs of the latches, which are always on, they always reflect what's ever in the latch at the moment, get passed directly onto these decoder driver chips. These are 7440s, I believe. Nope, I was wrong. 7441s. They are designed for things like driving Nixie tubes. It's a decoder driver, so the decoder part takes the BCD signal in 4 bits and translates that into a 1 of 10. There are 10 outputs numbered 0 through 9, and only one of them can be on at a time according to the function of the logical decoder in here. It's also a driver because those 10 outputs have driver capability to drive the Nixie tubes. And since the Nixie tubes are actually powered from the high voltage power supply up here through current limiting resistors, whichever output is turned on provides a path to ground for current to flow from the anode of the Nixie tube out the selected cathode into the driver circuits of the decoder driver chip and then to ground, thereby providing the current path, and therefore the current cathode that's got current flowing through it will illuminate. And those driver circuits are designed for higher voltage, as they would need to be, because you're running with a circuit that's well over 100 volts, but the current is very low. Well, you may say, well, what happens if the frequency input is so high that during the gate period it overflows all of these, and the overflow output of the last decade counter turns on? Well, they put another flip-flop out here. Think of it as another first stage in a decade counter. So this represents an additional divide by 2 or a storage, a 1-bit storage register. and it's reset along with everything else, and its input is toggled by the overflow of the previous one, and its output feeds into this little circuit, which is a gated latch, and it's gated by the transfer. So both the overflow that's been latched in here and the transfer feed into this. And it's a set reset kind of a flip-flop, very simple, and then with the control gates feeding into it. This gets set just the same way as the memory latch would work, except it's only 1 bit of storage instead of 8 bits of storage, or I'm sorry, 4 bits of storage there, or 8 bits of storage, 8 bits of storage. It's performing the same function, but it's doing it with a more discrete level logic, because all you need is the one bit. Now, I think that's kind of odd, because this is a 14-pin IC, and all 4 of these gates are in another 14-pin IC, so in terms of real estate on the circuit board, it doesn't make any difference. They could have just used another memory latch of 4 bits in place of this, and it would have taken up the same amount of space. But probably this is a less expensive chip than one of these, and they could save a few pennies per kit by putting it in that way. Don't know. So this registers the fact that you've had an overflow. Looking back at my little diagram here, what if you did count up to 99999, ignore the fact I put zeros in there, and the next input pulse comes in and it rolls it over to 100000, that 1 that would now be in the next decimal place over here, that's what gets captured here. And that turns on this transistor, which provides a path to ground from the high voltage supply through the current limiting resistor through the, actually it's more than that, this is actually a voltage divider from the high voltage supply to ground. So some lower voltage is available here, and then that causes current to flow through the overrange neon bulb through the transistor to ground, turning that on and saying an overrange. And because of that, this frequency counter, even though its Nixie tubes only read up to 5 digits of 9s, if you had it counting up near its maximum count, and then you got an overrange, that can be treated as a 1 in the next most significant position of the display, and then the counter keeps counting, you know, because the frequency is higher, the gate still hasn't expired, so it continues counting, but it resets once it rolls over, so you have an implied 1 in the next position, and then whatever count happened after that is displayed on the Nixie tubes up until the gate runs out. The gate period is over. And that's really the only dynamic indicator on this counter. There are 2 other neon indicators, and they are the ones that just reinforce whether you're currently in the megahertz mode or the kilohertz mode. 2 more neon bulbs. They're powered once again from the high voltage supply, this time without a resistor voltage divider. It's just got the current limiting resistor, and depending whether the range switch is in the megahertz mode or the kilohertz mode, one or the other of those lamps would be illuminated. So there's just a little bit more going on here. The gate signal goes into this cluster of 4 more NAND gates, as does another signal coming from switch selected interstitial points in the counting process in this gang of the range switch. In megahertz, it's just picking off the 1 kilohertz signal, and in hertz, it's picking off the 1 hertz signal, and that's getting switched into the gates. And between all 4 of them, they're logically combining those signals, and then they're generating the negative going reset, the positive going reset, and the transfer signal that moves the counted value from the counters into the memory latches. And how come these transistors here are shown in dotted lines? It's because, where was I back here? One of these ICs. Oh yeah. This is part of IC23, part of IC23, part of IC23, and there's another one somewhere. Oh yeah, Heathkit didn't show it because it's not actually being used, but there's the fourth part of IC23. But there's also two NAND gates that are in IC22. And what that actually has, it's only got the two NAND gates, but it also has two transistors built into the package, which can be used to drive circuitry that maybe has a greater fan out than the IC by itself can handle or something. Anyway, so instead of putting discrete transistors in, they're taking advantage of the fact that this particular IC, IC22, has these two transistors built into the package. So the reset signal turns on the one of them, and that provides an inversion, logically speaking, and that's how we get the complementary reset signal out here. It's naturally a low-going signal. This flips it to a high-going signal for the positive reset. So that's what that one's being used for. And then the output of this logic that's generating the transfer pulse, that's also conditioned by this, and it's working the same way. It's providing an inversion. This signal here would have the wrong logical state. It would be high when it needs to be low, and vice versa, just by the way it was developed. So it needs to be inverted again. There's no other IC in here that they can invert with. Oh wait, but there is. They're not using this quad part of IC23, which could be used as an inverter, but they chose not to do it that way, and they're using this other spare built-in transistor to do it. And then that's going over here and providing the transfer or latch function to all these latches. I think I've explained just about everything about this circuit, except for this one little bit here. They give you a test point so you can test the current frequency without having to open up the case and get out probes and things. So it's just a insulated screw actually on the case. It's not even a jack. It's just a screw that passes through an insulator on the rear of the case. And it takes this 1 megahertz digital signal and it runs it through an inverter made out of one of the NAND gates. And they screwed up here too. Number one, they showed both inputs of this tied together, which they're not. Pin 5 is actually tied to V plus or logic plus, and only pin 4 is tied to the 1 megahertz signal. And they actually showed it with pins 2 and 12, which is totally incorrect. Big drafting screw up there. Hence my correction. I got all this by tracing out foils on the circuit board when things started to look fishy. And then the output of that is, well, this is a more or less symmetrical waveform over here. And by inverting it, you don't really change it. It still looks the same. And then we have a lowly 500 ohm trim pot with a 100 ohm resistor in series with it. So regardless of how you adjust this trim pot, even if you adjust it to the point where it seems to be 0, there's still some resistance there. And it's really just a big voltage divider. And you're tapping off of it. And you can get whatever voltage level you want to have for your test point. And then you can put a oscilloscope on it or something, or the probe of another frequency counter, and use that when you're dialing in the trim capacitor down here to get exactly 1 megahertz for the clock. Alright, I've sketched out a design for a 3D printable light shield. And then because it needs to have a surface that can sit flat and not leave any overhanging surfaces like this orientation would, I've tipped it so this is the bottom. Therefore it'll print this as a base and then just print these narrow walls. It's 4 rectangles, or cubical rectangles, whatever we want to call those. They're not cubical, but 3-dimensional. And so I've done my usual thing with Tinkercad here, which I use for these simple projects. So far I haven't found a project that I can't do using Tinkercad, so that keeps it simple. I've made each of the 4 pieces a different color for ease in visualizing their overlaps and things like that. And this part here, which is the top, has 4 negative space holes in it of 4 millimeters diameter each. And they are the thickness of the 1 millimeter panel. Everything is 1 millimeter except for the base, which is 2 millimeters, just to give it a little more anchor. So now I have to drag those into position. I think what I'll do first is join these 3 together over in this area, and then group them, and then drag them into position on the base. Alright, everything's on a 1 millimeter grid, and every part is in even millimeter increments just to keep things simple, so I can just tap this over. Yep. Okay. Everything's in orientation now. We can see the holes as holes now instead of just the negative space symbology. We can see the workspace grid through them. So I'm just checking all angles to make sure that everything looks good. Looks like everything's lining up. And hopefully I haven't screwed up my design at all. And there it's imported into my Prusa slicer. It's looking like it came through unmolested. And it's been sliced, and I'm going to export the G-code and figure out where I'm going to put it on my computer. Alright, so it looks like the G-code has been created. G-code. So I've moved the G-code file over to my Prusa 3D printer, and I'm just waiting for the hot end and the bed to get to the proper temperatures for starting. We're nearly there. The hot end is just a few degrees low and the bed is a few degrees high. It's predicting 1 hour and 20 minutes to print this, which is about 10 minutes less than the time I have available before I have to head out to play in a gig this afternoon. Okay, we're just about there. It's doing its calibration. It's going to print a bead to clear out the hot end nozzle, and then it's going to start with the skirt. Can't hardly see anything yet. Well, I'll just let this thing do its bit. About 30 minutes to go, but good progress is being made. So far it's looking good. I was a little concerned about the holes, but it looks like they're coming out just fine. It's just finished making the third hole and is roofing it over at the moment. I feel like I should be playing Also Sprach Zarathustra. Looks like the monolith. Alright, it's done. There's a bit of a hair hanging off of it there. And it snaps off. Looks like it came out all right. All right, let's see if this goes in there, or if I totally screwed it up. There we go. It's not really held in by anything except gravity, but it does seem to fit in there just fine. Alright, flashlight from the rear. It's effectively blocking light from getting through. And if there's light from the front, it's not illuminating anything inside the frequency counter. And that's the goal of the light shield.